Hello, welcome to our channel for probability and statistics. In this video, we will talk about Weibull distribution and failure rate. So what is Weibull distribution? So Weibull distribution is a continuous probability distribution like exponential and gamma distribution. Weibull distribution is also often widely used to model the random number of time to failure, lifetime, like this kind of events. And the Weibull distribution's density function is fx alpha beta, the two parameters alpha beta x beta minus 1 times is minus alpha x beta in power for variable x larger than 0. So Weibull distribution is also only for positive random variables. So if we let beta equals 1, so Weibull distribution becomes to exponential distribution. So exponential distribution is a special case of Weibull distribution. And we have learned exponential distribution is also a special case of gamma distribution, right? And for the Weibull distribution, when beta larger than 1, so the density curve becomes somewhat bell-shaped, but has little skewness. So when beta larger than 1, it resembles the normal curve, but not normal because the curve has skewness. So this figure shows 3 Weibull distributions density curve. For example, beta 2 is 2. It looks like a normal bell-shaped, but not normal. And beta 3.5, it's very close to normal, but not normal because it has a little longer tail to the right side. And the mean of Weibull distribution is this form, and variance sigma square of Weibull distribution has this form, quite complicated. So this is gamma function. So like the gamma and exponential distributions, the Weibull distribution is also applied to reliability and life testing problems, such as the time to failure or life length of a component measured from some special time until it falls. So let us represent this time to failure by the continuous random variable t with probability density function ft, where ft is the Weibull distribution. And the Weibull distribution has inherent flexibility in that it does not require the lack of memory property of the exponential distribution. So we know exponential distribution is very specific because it is memoryless, or say always young. So for example, you have bought a new machine, but when you have used 1 year, it has no problem. If it follows an exponential distribution, so after 1 year, if it has no problem, just the same as you have bought this as a new one without having used 1 year. So this is called a memoryless or always young, always new feature of exponential distribution. And for the Weibull distribution, the cumulative distribution function CDF has this form 1 minus e minus alpha x beta. So fx, which means the probability of big X larger than this X value, right? Let's take a look at an example. The length of life X in hours of an item in a machine shop has a Weibull distribution with alpha equals 0.01 and beta equals 2. So what is the probability that it falls before 8 hours of usage? So the solution is we want to calculate the probability of x less than 8. So this is equals F8, right? We have shown in the previous page, F8 is the cumulative probability of all the random variables less than 8, right? So we just fill in alpha beta in the form, we'll get probability is about 0.473. So about 0.473, the probability that this machine item will fail before 8 hours usage. And now we will talk about failure rate for the Weibull distribution. So when a Weibull distribution applies, it is often helpful to determine the failure rate. So failure rate is also called hazard rate, in order to get a sense of wear or deterioration of the component. So we will show what is the failure rate. So let us first define the reliability of a component or product as the probability it will function properly for at least a specified time and specified experimental conditions. Therefore, reliability is designed to be the reliability of the given component at time t. So we may write reliability of any component is the probability of it lasts larger than this t, right? So it actually is the integral of the density function from t to the infinite, positive infinite. So it equals 1 minus ft. It's quite understandable because if it has no problem, no failure until time t, so this is the reliability, right? So, but ft is the probability of it lasts less than time t. So that's why the reliability is 1 minus this cumulative probability ft, right? So where ft is the cumulative distribution function of t. And then next we will show the conditional probability that a component will fail in the interval from t to t plus delta t, given that it survived to time t. So next we will calculate one item. So after this element has survived to time t, but it will fail in the next delta t. So this calculation is ft plus delta t minus ft divided by rt. So rt is the conditional probability in the denominator. So given this event has occurred, the next what happened is the probability between these two is the cumulative probability of t plus delta t minus the cumulative probability of ft. So we further dividing this item by the delta t, because this delta t is not specified how much. So we just divided by the delta t, we'll get the unit ratio of this item. Then take the limit as delta t to the 0, then we will get the failure rate. So failure rate called Ct equals limit delta t to 0, then cumulative probability between these two items divided by delta t, then divided by reliability of t. So after mathematical manipulation, we'll get failure rate equals the density function t divided by the cumulative probability of t. And for the Weibull distribution, because this is for odd distribution, so for Weibull distribution, we just fill in the Weibull distribution's density function and the cumulative probability function, then we'll get Ct equals alpha beta t beta minus 1 for the hazard rate, for the failure rate, for any time. So we can calculate for any time t, its failure rate. It's a failure rate. So this failure rate for the Weibull distribution is quite interesting because the quantity Ct is actually named as a failure rate since it does quantify the rate of change over time of the conditional probability that the component lasts an additional delta t, given that it has lasted to time t. So failure rate is measure how likely it will fail if it has used time t, but in the next very small delta t. So this is say we have lived 1 year, but what is the death rate from this point? You ask such kind of question. So this is called the rate of decrease or increase with time is important. So the following are crucial points. In the Weibull distribution, if beta equals 1, we can get failure rate is alpha. If we look back, beta equals 1, so Ct equals alpha, right? This means because beta equals 1 is the exponential distribution, this means for the exponential distribution, lack of memory, the failure rate is constant. No matter how long it has been used, 1 year, 10 years, it has survived. From this point, its failure rate is off, is constant, is unconditional on the time, how long it has survived, right? So exponential distribution has a constant failure rate at any time point. But for beta larger than 1, in the Weibull distribution, Ct is an increasing function of time t, which indicates that the component wears over time. If we look back again, beta larger than 1. So this term large than is not constant, right? Will increase over time. Because beta larger than 1, so the power part larger than 0. So when t increase, this term will also increase, right? So for the beta larger than 1, it means the component will wear over time, will more likely to get failed, more likely to die, like such more likely to get failure after time longer. And on the contrary, if beta less than 1, for the Weibull distribution, Ct is a decreasing function of t. That is, the component will strengthen over time, which means the component is less likely to fail with the time longer for beta less than 1 in Weibull distribution. So for example, in the previous example, in a machine shop, as a Weibull distribution with beta equals 2, then we get a failure rate is Ct equals 0.02 times t, which means when t is larger, longer, Ct will also longer, right? But on the other hand, if we set beta equals 3 or 4, alpha 2, so in that case, Ct failure rate equals 1.5 divided by t, 1 of 4 in power. So when t is bigger, this Ct will be smaller, right? Because t is in the denominator. And that's why it gets less likely to get failure when t is longer, right? So this means the component will get stronger over time. Thanks for watching.